this is the next part of reaction rates. So once we know about how fast things go, we have to know how many steps it takes to get there and what that pathway looks like and all the rest of it. So one of the things I didn't talk about when we talked about reaction rates is that I cannot, under any circumstances, use the stoichiometry of that reaction to determine my reaction rate. Notice that we did all of that with calculations. Okay? So the stoichiometry of my reaction has nothing to do with it. And you'll see today why that's the case. So let's go ahead and share so that we can get this started. And this is a much faster than the last one. So hopefully this won't take forever. And I think I've thought great. I love it when I do that. So let me share that. Oh yay! Now we're on the right page. Awesome. So we're going to be talking about mechanisms. But before we talk about mechanisms, we need to do a little review. So, how do we measure the rate of a reaction? What is the way that we talk about it? Well, measuring the rate of a reaction is change in concentration, change in time. If it's a reactant, it's negative, and we always have 1 over the stoichiometry to do that. So that's how we measure the rate, change in concentration over change in time. What factors affect the rate of the reaction? Well, I'm not going to list them all. There's a whole side of things that affect them. Temperature is one of them. Physical, like what phase it's in. So, gases are the most free to move, but they don't collide that much. Aqueous stuff is more available. Things that's in the solid form, more surface area it has, that's more favorable. Thinking. Catalysts affect the reaction rate, and concentration. So what our concentration is. What is required to get a product during a reaction? Well, that's an interesting question. There are 3 things that I've mentioned. So I need a collision. That collision must have sufficient energy. EA, that energy barrier, needs to be met. The other thing is that I need the proper orientation. If I hit in the wrong way, I'm not going to be able to get that reaction. So those are 3 things. I typically list collision, then EA, and proper orientation after it, because if I don't get, the collision and the EA, then I've got nothing. Activation energy. Activation energy is EA. So if we talk about one of these graphs that we had, the EA is the difference between the energy I start with and the energy up here at this highest point. So that's my activation energy. So EA. Transition state is the thing that exists at that highest energy point. Okay, we can call it reaction intermediate. We can transition state, activation. Another phrase. Activated complex. That's the word. Sorry, activated complex. So that's what we're talking about. And it actually is a transient species that we cannot measure that is partway between reactions and products. Okay, it's neither one of them, it's partway in between. Now, an intermediate is something that I cannot measure, is something that I can measure, and it happens in between a couple of different steps. Okay, we haven't talked about that yet, so I don't know why that's there, but sorry, that's what that is. A relative reaction rate is one that is just specific to a given component. So it's missing that part right there where we've done the correction for a reaction or product and the stoichiometry. We can measure an instantaneous rate as the slope of the line that is tangent to the curve at any given time. An average rate is the change in concentration versus change in time. Doesn't matter what the time limit is. An initial rate is that instantaneous rate at the very beginning of the reaction, so time equals 0. And the heat of reaction is how much energy it takes to get from my products to my reactants. And that's either going to be energy I have to put in or energy that needs to be given off. Okay, we talked about the 2 terms for that. So I need to put it in, that's endothermic, and if it needs to come out, that's exothermic. So that's the heat of my reaction. In a reaction, I double the concentration of the reactant, and the rate goes up by a factor of 4. So if I change my concentration and say, okay, well, it's 4 here, it's 2 there, and here it was 2, and now instead of being 4, it's 8. That's what we're talking. So if the it goes up by a factor of 4, then that rate, or sorry, the order is 2. If the rate doubles, then that order is 1 because my concentration has doubled. So we did the exact same thing so that that order is 1. And what if the rate doesn't change? If I change that concentration and nothing happens, then that order is 0. Okay? So those are the relationships that we're looking at there. We did mathematics to be able to talk about that. Here is a qualitative explanation of that. So that's what we're dealing with in those terms. Okay. Go off. All right. So that's our review. So now that we've done our review, I'm going to go ahead and okay, I'm going to go ahead and stop sharing and I'm going to stop recording, and I will see you again in a couple minutes. Thanks, guys.